Okay, so today we will look at a very important concept in radiative heat transfer, namely black body, the definition of black body, its properties, right, and then this is central to the study of heat transfer. It is like the definition of God and looking at the properties of God, because it is essential to understanding spirituality, right. So like that black body is a benchmark. So there is no perfect black body in the world. Do not extend the argument in saying that whether it does it also mean that so we define the properties of real surfaces based on some benchmark. That benchmark is the highest, always getting CGP of 10 in all the semesters, okay. So something like that is the black body. So we have to formally define the black body and look at some concepts underlying this definition and also some of the properties, and then we look at solid geometry, and once you have a definition of black body and then this solid geometry, then we will go on to the radiation laws, namely with Planck's distribution, before that the Rayleigh-Jeans distribution, the Wien's displacement law, the Stefan-Boltzmann's law and so on, then it will be followed by properties and so on. Now black body, what do you think a black body is? Absorbs radiation at all wavelengths. Other bodies also absorb radiation at all wavelengths. Does not? It also allows it to go through. Therefore, your definition is partially correct, but not, it is not fully correct. Absorb and emit is a different story. Don't forget, don't talk about emission already.
Absorbs 100% of all radiation.
Absorbs 100% of all radiation incident on it. No, it allows 100% of radiation incident on it onto itself and internally absorbs all of it. There are two parts to the definition. It allows all the radiation to enter it. It internally absorbs, so not even 1% goes out. So what does it imply technically? Reflection equal to 0, transmittance equal to so black body is 1. So black body is one that allows all incident radiation and internally absorbs all of it, okay. We will use some color, if it is too bad you tell me, okay. Is it okay? 0, so this definition requires further qualification because it allows all incident radiation, internally absorbs all of it, is true for all wavelengths, okay, all incident directions. So this is valid for all wavelengths and it is valid for all incident directions. So therefore for a given wavelength and in a given incident direction, there cannot be any body which absorbs more radiation than a black body. Any real body has to absorb a radiation which is lower than that of the black body. Now if you ask a question, How do you know what is the maximum that can be absorbed? That comes from theory and it is verified by experiments and all that. Now it is basically conceptual definition. We introduce something called a benchmark. So this concept of maximum absorption regardless of the incident direction and regardless of the wavelength is central to the understanding of radiative heat transfer. Okay. So the black body serves as a benchmark with which all the other real surfaces can be compared. Now incidentally the black body also emits the maximum radiation for a given temperature. This is a consequence of this that can be proved. So some people, as Pradeep Kamath defined, he said black body is one which emits a maximum amount of radiation. That is true, but that cannot be used for defining the black body. A black body is fundamentally defined on the basis of its ability to absorb fully. That it is emitting maximum is a consequence of the first, it is a corollary. First law of thermodynamics, Q minus W is equal to delta E. For a cyclic process, Q is equal to W. Okay, that is only a subset of the general law of Q minus W is equal to delta E, because you do not know what happens when Q is not equal to W. When Q is not equal to W, what is the story? It is equal to the change in energy of the, so that is more general than this. Are you getting the point? Therefore, that a black body is capable of absorbing completely is the fundamental basis, is the fundamental premise on which the concept of black body has been proposed, right. Now example, some examples, ice is 0.98, okay, emissivity, ice is comes very, so we will list ice later. Something called platinum black, lamp black, platinum black. Some special paints which come very close to that, right. So suppose you want to do experiments in heat transfer lab, okay, not necessarily heat transfer lab of IIT Madras, somewhere you want to do experiments, you want to realize this black body, what you can do, probably you will take some aluminum plate or something, you will coat Asian paints, you go and buy one and take a brush and coat it and let it dry, or if you are rich enough you can do the spray painting. Now you measure the emissivity, it will give 0.8, 0.88, 0.9 and all that, because there will be some places where you have not fully coated. After it dries, second coat, maybe it will go to 0.92. After then it will asymptotically saturate, you cannot get that 1.00, but you will get something like 0.9495. For all practical purposes it is a black body. If you want to do experiments, you can say it is a high emissivity body. Okay. Now why this name? Why can't we call it white body? Black is after all a bad color. Therefore,
all radiation is
If no wavelength is reflected from it, how can you have it?
there is no way you can see it because everything is
Everything
absorbed.
generally are very poor reflectors, right. Hence they appear to be black. Appear to be black from what point of view? They appear to be visually black. But the eye is a very poor instrument to detect radiation, because you can detect only in a very narrow range of 0.4 to 0.7 micrometer. So it may be very black between 0.4 to 0.7 micrometer, but other parts of the spectrum, what is the story? You are not in a position to, you need sophisticated, you need a spectrometer and this thing, and to find out its behavior. But since the visible part of the spectrum is genuinely a part of the electromagnetic spectrum, if something is truly radiatively black, between 0.4 to 0.7 also it will be black. Therefore, all radiatively black bodies have to be visually black. However, all visually black bodies need not be radiatively black, because we do not know. Did I confuse or did I clarify? If it appears black, it is black in 0.4 to 0.7 micrometer portion of the spectrum. It may have a good emissivity, but I cannot say it is a perfect black body, because the eye is a poor instrument to detect whether to find out whether something is a black body or not beyond that 0.4 to 0.7. We are getting that point. But a radiatively black body has to be visually black, but a visually black body need not be radiatively black. In fact, a radiatively black body like ice is actually white in color, because unfortunately for the certain portion of the spectrum alone it is doing some reflection. The other portion of the spectrum, it just absorbs everything. That is why people are crying hoarse, no, this climate change and all that. If the ice melts, because there is a difference in the reflectivity between the ice and the water, if there is a change, if more melting takes place, then it leads to what is called a runaway effect. Let us not get into climate science now, some of you have taken my atmospheric science course, so you know this. So therefore, there is a big deal about this reflectance of ice and water and all that, what happens when melting takes place. Okay. So let us conclude by saying this discussion by saying that converse not true, it may or may not be. Okay. Now what are the properties? There are other how do you know there is something ideal concept called black body? Why is it necessary to figure out this concept? Why bring in the concept of black body at all? Huh? For comparison purpose, and also to describe radiative properties of various substances. Therefore, the black body, the theory of black body proposed by theory, the theory of black body and the properties are proposed by theory. So the black body is originally proposed by theory. What is that theory? What theory is it? In physics, quantum mechanics. Okay, it is proposed by quantum mechanics, and it has been verified by experiments done by so many physicists, right? What are the basic key? The key attributes of a black body. it's a perfect emitter. Perfect absorber is already there in the definition.
So if black body is a perfect emitter, then it should have a color.
Right?
It will glow.
No, why? Emission is only if you are looking at the reflection point of view. That definition of black body is from a emission. Any body will continue to emit radiation so long as it is at a temperature above 0 Kelvin. So if you are looking at the emission color, what you are saying is correct. Okay, if you are looking at the reflection color, my shirt is red in color, not if it is emitting red I will die, and what is the temperature? Means displacement law, I will tell you, I can't survive. So it is basically because this stupid shirt, whatever. So it absorbs all the colors except this red.
So at high temperatures it has to be.
Yeah, so that is that emission color, color based on emission. We use it in pyrometry. I will teach you a little later. Any other question? Okay. So it is quite tricky. Quite discussion of black body and all that is quite philosophical. After that it will get numerical, of course. Then we will keep on solving equations and all that. But first part at least is like this. So let us consider. Now we have to do some thought experiments. Okay. Let us consider an evacuated enclosure. Right. The evacuated enclosure is at a temperature of T infinity. Okay. So there is vacuum inside. Now I put a black body, small black body. Black body initially at TW. Okay. So I am saying that TW is greater than T infinity. The black body is not touching the walls of the enclosure. So which mode of heat transfer is prevented? No conduction. So it is evacuated, so there is vacuum, there is no medium. So which other mode of heat transfer is prevented? Convection. Okay. But TW, let us say T infinity is 30 degrees centigrade and TW is 200 degrees centigrade. It is a small body. It is a small body in a large enclosure. After sufficient time has elapsed, what will happen? Okay. What temperature? I am saying that the enclosure is an infinite heat sink, for example. Suppose I put for the argument that the heat received from this small body will not affect this enclosure, then eventually equilibration will take place. The black body will achieve equilibrium with the surroundings. Eventually, so you have something like this. Okay, so it reaches T infinity after sufficient length of time has elapsed. Okay. Now, thermal equilibrium is established in the enclosure in which, in an evacuated enclosure in which a black body is present, but the small object is a black body. So what is the story there? It is absorbing exactly the same amount as it is emitting, because if the emission is not equal to the absorption, then there is a net rate of change of enthalpy which has to take place inside the black body, as a consequence of which its temperature has to go down or go up, which is again forbidden because already equilibrium has been established. Therefore, the amount of radiation which is emitted by the black body is exactly equal to the amount of radiation which is absorbed by the black body. Since it is a black body, it is absorbing the maximum amount of radiation. therefore it is also emitting the maximum amount of radiation. How do you like it? The shady proof, but don't ask me, sir, what happens if you don't have the enclosure and all that. I know to prove it only with the enclosure, but it is good enough. Okay, don't ask me to repeat, I will distort it. Okay, so it has achieved, to cut a long story short, it has achieved equilibrium with its surroundings. Now there is no convection, no convection, no conduction. So the amount of radiation falling on the body is equal to the amount of radiation is going out in terms of emission. Emission is equal to absorption. Since the absorption is maximum, not because it is experimentally verified whatever, because I already declared it is a black body. So since the absorption is a maximum, emission is a maximum. So if it is a perfect absorber, it goes without saying that it is a perfect emitter. Okay, so all those stories you can write. Now we will go to the next one, perfect emitter. So I will write emission absorption is max, therefore emission is max. Yeah, it can be proved. It can be proved for a non-black body also. That is in the enclosure. If it is only in enclosure.
Sir, even if it is not black body.
No, even if it is for a, even if it is not for a non-black body also it is true. It does not automatically mean for a black body it is not true. I am not saying that it is true only for a black body. It is true for a black body.
Bodies, no.
The strategy now is, before you can think about it, I will go to the next one. But I will clarify. What is your problem?
It's true for any bodies. Why black body? At steady state, all the even both are in infinity.
It won't be absorbing the maximum. It will be equal. That's all. But I cannot put for the argument of maximum. The equilibrium anyway, absorption is equal to emission. There is no doubt about it. But the non-black body is not absorbing the maximum. That it holds good for a non-black body does not prevent us from saying that it holds good for the black body. What is the problem? All that is okay, Vinay, let it do whatever it wants. But what happens at equilibrium? Let it do whatever it, we give it freedom. You can take pass fail, self study, whatever. Eventually you have to get 160 degrees. Huh? Huh?
We are only concerned with the equilibrium behavior.
We are concerned with the equilibrium because I may be interested in the non-equilibrium also. Anyway, you are doing your assignment, right? That is about non-equilibrium. But here I want to prove something. Okay, we did not do the experiment, it is only thought experiment. We do not have to spend so much time on this. Okay, fine. Yeah, I did not tell you because I know that it is valid even for a non-black body, but that is okay. Radiation isotropy. Okay, suppose the story is like this, it is T infinity, TW at T equal to 0, right. I have one more case where it is the same enclosure and the same black body, but I am keeping the black body here. It is same TW at T equal to 0. Is there any change? So long as the enclosure temperature is at T infinity and the body, it is a small body placed in large surroundings where the large surroundings have infinite capacity to take on the heat, regardless of the position of the black body, it will reach the same equilibrium temperature. Upon reaching equilibrium, the emission will be equal to the absorption, and that will be maximum corresponding to the temperature T infinity. Since it is independent of position, therefore you can rotate, you can keep it wherever you want, it is independent of the position or the orientation of the body. Therefore we say that there is radiation isotropy within the enclosure, within the enclosure a uniform radiation field has been established. Okay. So, the radiation isotropy means radiation field this black body is inconsequential. This black body is only a tool, it is only a prop for me to prove this. Even without a black body I can have a cavity like this which is at TW, which will be generating radiation because it is at a temperature greater than 0 Kelvin, consequent upon the previous law it will continue to emit radiation. So if I have a cavity like this, I close the cavity on all sides but only have a small hole, and if I heat it, so an evacuated cavity which is heated and which is maintained at vacuum, which is a small hole, the radiation field emerging from it would be isotropic. That means it will not have a direction dependence. When the radiation is coming out, it will have a uniform intensity in all the directions. That is a radiation isotropy. So this radiation isotropy is related to what is called the hole run. Hole room means empty room in Deutsch, that is German. The hole room concept can be used to mimic or simulate a black body under laboratory conditions. If you want to simulate a black body, instead of doing 4 or 5 coats of paint, you can build a cavity and close it on all sides and have a small hole. Evacuate the cavity and heat it with a nichrome wire or all that all over the place, and then the pencil of rays which is coming out from the top hole or wherever it is, that is basically an isotropic radiation. It is equivalent to radiation from a black body corresponding to the temperature of the enclosure. Okay, fine. Perfect emitter in every direction. How do you prove this with this enclosure business? Suppose I have T infinity. Now I have only one small area. I have only one small area dA which is active on the walls of the enclosure. All the other areas are not radiatively active. Even then, after sufficient time has elapsed, an equilibrium will be established and the body will also cool down to temperature equal to T infinity. Now the body will continue to absorb radiation and this radiation will be maximum because it is a black body, but all the radiation is coming in a particular direction because only one portion of the enclosure wall is active, and it has to radiate back the same radiation, because if it is not so, then equilibrium will not be established. Therefore, since it is absorbing the maximum in that particular direction, by consequent upon we RGing the black body by making so many portions of the enclosure wall invalid, it has to radiate the maximum in the same direction. Therefore, in a particular direction also it will be the maximum emitter. So this is, and since it is anyway the same in all the directions, it is maximum and equal in all the directions. Okay, these are not required for solving the problems and all that, but this is the conceptual clarity is very difficult. No, I will not ask any question on the exam from this, but it is central to your understanding. Okay, because you can solve problems without understanding. Okay, I am putting forth one argument. I mean, it can get radiation. You can design an experiment where it can receive radiation only in a particular direction. It gets heated, but eventually it has to get cooled. because that is the, I mean, from the second law of thermodynamics. But when it is radiating back, the enclosure will not accept radiation from any other direction, so it has to radiate in that direction. In that direction, emission must be equal to the absorption. Since it is absorbing maximum consequent upon it being a black body, it is also emitting the maximum in that direction. But as a consequence of the radiation isotropy in the enclosure, it is not only maximum, it is also the same in all the directions. Okay, right. Before you get further doubts, we will move on to perfect emitter in every wavelength. Now I can design this, I will do the same thought experiment, but now the walls of the enclosure are so designed that it will emit radiation or it will absorb radiation only in a very small wavelength interval of d lambda about lambda. When it is doing that, this poor black body will also absorb radiation only in a small wavelength interval d lambda about lambda, okay, while it can continue to emit radiation in any other direction in any other wavelength, but the walls of the enclosure are in a position to absorb radiation only in the same wavelength interval d lambda about lambda. Therefore, whatever it absorbs must be equal to whatever is emitted, otherwise equilibration will not be established, and this d lambda about lambda is purely under my control. I can change this d lambda about lambda at my will. This lambda can be in the infrared, ultraviolet, whatever. Therefore, it should be valid for any d lambda about lambda. Therefore, at every wavelength it will be the perfect emitter. Okay, fine. Now E, you can fill up. Suppose you have an enclosure like this, T infinity, and you have a black body TW, you start the experiment. Same thing, vacuum, no conduction, no convection. What will be the eventual equilibrium temperature reached here? T infinity, here T infinity. So the characteristics or the shape of the enclosure do not affect the eventual equilibrium temperature. Therefore, the radiation field inside a black body does not care a damn about what is its shape, size and all that. So long as it is evacuated and fully closed, it will continue to emit radiation, isotropic radiation corresponding to its temperature only. Therefore, black body radiation, whatever you want, intensity, whatever, that we can see later. Black body radiation strength is a function of T only. So we have covered a lot of ground, right, at least 5 attributes, right. Now one more question we have to answer before we move on to solid geometry. Where n is greater than 1, for example, n is not negative, whether the radiation strength increases with temperature or decreases with temperature. The answer is so obvious, it decreases with temperature. Oh, it increases with, it increases with temperature. This is what happens when you keep on arguing so much about something. Okay, how do you prove it? How do you know that it is a monotonically increasing function of temperature, the radiation strength? That is, if there is a black body at 300 Kelvin, it is emitting some black body radiation. If there is some other black body at 500 Kelvin, it is emitting some other radiation strength, intensity or flux, whatever. How do you know that for the 500 Kelvin it will be more than 300 Kelvin? Now something tells you, no sir, it is T to the power of 4 whatever, but right now we assume that we don't know that it is proportional to T to the power of 4. Now we can again do a thought experiment. So we can consider two plates which are at temperatures T1 and T2, okay, and the radiation strengths are E1 and E2. I will assume that T1 is greater than T2, but for a change I will assume that E1 is less than, assume. So it is evacuated, no convection, no conduction, only radiation is taking place, evacuated. Now if E1 is less than E2, then what is the direction of flow of energy? So Q equal to E2 minus E1, so it will flow from this. So you have a positive transfer of energy from a body at a low temperature to a body at high temperature, which is forbidden by the second law of thermodynamics unless you are able to transfer some work. Therefore nothing in this argument is wrong except our original assumption that E is proportional to 1 by T. Therefore the original assumption should be wrong, therefore E has to be a monotonically increasing function of temperature. So such ways of proving something by proving the false to be absurd is called reductio ad absurdum. You heard about it? Reducing to absurdity. I talk about it in ID 110 also. How do you prove that root 2 is irrational? Assume that root 2 is rational and keep on getting something, finally you come to some conclusions and that conclusions are unsustainable. Then you go back and say all the steps are correct except my original assumption that root 2 is rational. Therefore root 2, like many of us. Okay, so now let's, okay, these are the attributes of a black body. Now what is the story? What is this E? We don't know. How does it, is it T to the power of 1, 2, 3, 4 whatever? We don't know. So many minds of the best of brains 100 years back were working on this problem, right? In order to derive this black body characteristics, that is the quantitative aspects of the black body behavior, it is imperative that we study a little bit of solid geometry. So solid geometry required to study black body characteristics. Okay, first we have to introduce solid angle d omega. Okay, so plane angle that is dl, right? This is the radius r. So d alpha equal to dl by r. Plane angle units radians. Okay, 1 this plane angle. So 2 solid angle. This is area DAN, that is area normal this is the radius r. Okay, this is a small elemental solid angle subtended by the elemental area dAn at a point on this. Okay, so d omega I will say an, the n subscript denotes a normal area. Okay, what are the units for this? Steradian. Do not put capital SR. Capital S, small r is strontium, the periodic table. What is the atomic number? Strontium is strontium 90. Strontium 90 is used in cancer therapy, radioactive. Okay, so don't make it radioactive. Already there is radiation. So lot of people use capital K for thermal conductivity. That is not correct. Capital K is reserved for Kelvin. Small k is thermal conductivity. Okay, this solid angle. So the first is solid angle. Next is we have to introduce a spherical coordinate system. Okay. So what is the spherical coordinate system? So let us consider okay. So there is an elemental area dA1 which is emitting radiation. Okay, it is going in all the directions. There is another elemental area dAn which is intercepting this radiation. Okay, so this is the now you can shine a torchlight on this, then its shadow will fall on the xy plane. Okay, then this angle is called the phi. Okay, and this, for example, this register is your basically this is your n unit vector which is vertical n, and this dA is like this. So this included angle, this angle is called theta. Okay, so theta is called the zenith angle. And phi is called the azimuthal angle. Is there a stick here? There used to be one stick. Oh, it is there. Okay, let us start from this. This is x equal to 0, y equal to 0, z equal to 0. This point, that is not clear. Is it okay? You are able to see? Okay. So this is x equal to y equal to z equal to 0, that point. So let us consider some dAn here. We shine light on it, so there will be a shadow. Okay, how it is? What is the deflection from the horizontal from one of the axes is basically your phi. That is, the phi is this angle, azimuth. Okay, but with compared to the vertical, how much is it deflected? That is the theta. So this theta phi is a very important notation which is used in radiative transfer. Okay, so zenith angle, and this you can on the coordinate system. You can have x, y, z, some point which is given by x1, y1, z1. This point can also be described, the coordinates of this point can also be described as you can also describe the coordinates of this point as r theta phi, where r is basically of course this is considered as 0 0 0, correct. So we introduce a spherical coordinate system basically for convenience. It is operationally convenient for us to understand concepts in radiation. Therefore the spherical coordinate system becomes imperative, it becomes essential. Along with the spherical coordinate system we have to include the solid angle because the radiation is spreading in a 3-dimensional fashion. Okay. Now can we revisit that DAN, can you write DAN in the r theta coordinates, that is DAN, and then take DAN by r squared. Can you get an expression for the elemental solid angle for a differential area dA1, put the differential area DAN, okay, in terms of r theta and phi. Maybe I can draw a figure and that will help you. Okay. Let us look at the solid angle subtended by the same DAN. So this is my dA1, okay. So now instead of putting the area like this, I can make it more clear. I will take a point here, okay. So this is d phi, right. Okay. This is r, this is d theta, okay. This theta, this is unit vector. Now what is this? R, good, r d theta. What about this fellow? So this is the area under consideration. So this is my DAN, please note. Solid angle subtended by an elemental area DAN at a point on DA1, where DA1 is that area which is emitting the radiation and DAN is that elemental area which is receiving the radiation. So you need a giver and a taker. DA1 is emitting surface, from there radiation is spreading in all the directions. Among all the directions we are taking on DAN, a small elemental area, and find out how much it is capturing and writing it in terms of the fundamental coordinates. Okay. As r keeps on increasing, the fraction it captures will keep decreasing, isn't it, for the same area. Okay. So this water bottle is generating radiation, okay. I am capturing the radiation with this chalk piece. This area is fixed, this area is fixed. If the chalk piece is moved far and away, what will happen to the amount of radiation which is falling on the chalk piece? Less, okay. And even at the same radius, depending on the direction, it can change. Are you getting the point? So you put it like this, it cannot do much. If it is vertical, it will. Now, what is this? So what is this now? Tell me. Very good. Already you are jumping the gun. It is r sin theta. So this fellow is r sin theta d phi. Therefore, d omega equal to DAN by r squared. DAN is r sin theta d phi r d theta 2. Therefore, d omega is equal to sin theta d theta that will be equation number 3. No r squared, correct. So what will be the total solid angle associated, what will be this total solid angle associated with the elemental area dA1, that is radiation is falling on to a hypothetical hemisphere above it. What should be the solid angle? I will just close in 2 minutes. Total solid angle so the phi will vary from 0 to 2 pi and theta will vary from 0 to pi by 2, sorry, hemisphere is pi by 2, sin theta d theta d phi so therefore the total solid angle associated with the hemisphere is 2 pi steradian, the total solid angle associated with the sphere will be 4 pi steradian. Okay. So total angle associated with the circle was 2 pi, the total plane angle associated with the semicircle is pi, hemisphere is solid angle, hemisphere is
2 pi,
full sphere is
4 pi.
Please remember this. We will close. Tomorrow we will find out, we will introduce an important concept called radiation intensity and we will work with solid angles and see how intensity, once you have intensity, how you can calculate flux. From finally we are interested in the flux, okay, but solid geometry is inevitable. Without solid geometry we cannot proceed. You can work with x, y, z also, but it is very tedious. It is better to work with r, theta, phi, okay.